apologize in advance. I might accidentally say the Iron Chef competition, of which of course I'm a big fan, and of which inspired this competition. Okay, this competition is also based on the very popular Iron Science teacher program run by the Exploratorium in San Francisco, USA, hence the top prize. 2005 is the International Year of Physics and also the centenary of the publication of Albert Einstein's seminal papers. The Science Center is currently hosting an exhibition called Albert Einstein Man of the Century in our Physical Sciences Gallery. I hope that all of you will be able to catch it sometime as it closes in December. This exhibition came from the Hebrew University of Jerusalem, Israel, and with much help from the embassies of Israel and Switzerland and the Swiss House Singapore. The Iron Science Teacher Competition is our anchoring event of the Year of Physics and is our clarion call to all teachers to celebrate these commemorations and to share and showcase their teaching techniques and abilities. Okay, without further ado, please allow me to invite Dr. Chew Tuan Cheong, Chief Executive of the Singapore Science Centre, to welcome you.
Thank you, Charlene, and good afternoon, distinguished judges, teachers, students, and colleagues. I'm really pleased that this particular competition is actually happening. Charlene didn't tell me that the top prize was a trip to San Francisco. Otherwise, I would have also seriously considered bribing the judges and taking part. But really, this is a competition that is long overdue in Singapore. It may interest you to know that this afternoon, somewhere else in the Science Center, we are also launching a different event. This is called Discover Science Resources, in which we provide science kits that can be loaned out to schools. Now, that particular exercise, where we become a science kit library, is also born of the same intention as this competition. And basically is this. We have discovered over the years that the teaching of science in the schools is one of the greatest hurdles faced by teachers, whether it's primary or secondary. Science is a subject which is quite abstract. It is not like language that's used in everyday life. And very often, the science teacher, especially those in primary schools, are not themselves fully equipped with the knowledge. In fact, no science teacher is fully equipped with the knowledge. So there's always a need to use some other techniques, like learning together with the students, like asking students to do research by themselves, and so on. So teaching of science is very challenging. To make it worse, students also may find it quite boring because it's difficult already, and then after a while you find that other subjects are more interesting. And it's in Science Center's mission to promote interest in science, to promote the proficiency of Singaporeans and Singapore students in science. So we felt there is something that we ought to be able to do if we can somehow raise, I wouldn't say standards, but raise the energy level in the teaching of science in the schools. And what's more important than the teacher? What's more important than being able to stand in front of a classroom and engage the students for a full lesson instead of losing them within 5 minutes by the time you start speaking? A competition like this actually is quite daunting for participants, because you are breaking new ground. In that sense, I think it's also very exciting. I had a bet with one of my colleagues that he was targeting something like 100 participants. I said, if you can get 20, you're very, very lucky. In the end, I was proven wrong. I think more than 30 people sign up, and at the end of the day, we still get close to 30. What is also very gratifying is the distribution is almost equal between primary, secondary, and JC. And we even have an English language teacher, I understand. So that's wonderful. Okay, the most powerful messages in history are transmitted by the spoken word, not by the written word, not by the mass media, but by somebody speaking to another person. So today we are going to witness the power of the spoken word plus demonstrations, hands-on experiments, and I don't know, maybe song and dance performances as well. I believe you'll all be entertained. I'd like to thank the organizers. I'd like to thank the judges for taking time off to join us and help us adjudicate in this competition. Okay, I hope the best person goes to San Francisco. I hope you all make it to San Francisco one day to see the Exploratorium there as well. I apologize for not having to stay for the full duration of this event because I have to be at the other event. But I'll try my best to come back and see as much of the competition as I can. Okay, thank you to the teachers for coming forward. And I think you should be proud of yourself in setting a new precedent today in the Science Center. We hope this will be an annual competition, although it started for the year of physics. We hope this will also extend beyond physics and physical sciences so that it becomes a great annual event, a festival which everyone can look forward to. Okay. And to everybody here, thank you so much for being here this afternoon. I hope you have a fun time. Thank you.
Thank you, Dr. Chiu. It's now my pleasure to introduce to you our distinguished panel of judges. We have Madam Linda Chua Mui Mui, who is the Head Science Branches Curriculum Planning and Development Division, Ministry of Education, Associate Prof. Chia Tet Fat from Natural Sciences and Science Education Academic Group, National Institute of Education, and Professor Andrew Wee Tai Shan from the Department of Physics, National University of Singapore. He's also the Vice Dean of Science. And Mr. Clarence Sirasina is our Science Center's Assistant Chief Executive, who will act as the moderating Chief Judge for today. Let us put our hands together and show our appreciation for their presence. Okay, before the contest begins proper, let me just briefly explain the rules to you. The contest is open to all teachers in all local and international schools and to the trainees of the National Institute of Education. Contestants need not be science teachers, but they must give a short lesson on a physics topic of their choosing. Each presentation must be in English. Each contestant has 1 minute to set up, immediately followed by 5 minutes to present, immediately followed by another minute to field any questions from the judges and or the audience, which is you. Each period is demarcated with the sound of the bell. As the contestants respond to your questions, is an important part of the judging process, we encourage you to ask more questions. There will be a short 5 to 10 minute recess around the top of each hour. After all the contestants have shown us their best, the judges shall retire to deliberate on the winners. Before we begin with the very first contestant, the Singapore Science Centre wishes to thank the Swiss House Singapore for their generous contribution to this event. You're all invited to enjoy the delicious handmade liqueurs and as well as the Ricola at the side of the table. And of course, there's some bottles of new water there as well. All right, so let the fun and excitement begin. Okay, we'd like to call upon our first contestant, Mr. Marcus Ang. Marcus is from Boon Lay Garden Primary.
Good afternoon to everybody. It's my pleasure to be here, and I can see a professor from NIE. Just a brief introduction. Okay, I just graduated from NIE just half a year ago, so I'm new into this profession. But I'm very delighted and extremely happy to see all, even the students at the back, who are the pupils who I always be in contact with. Hey, today what I'm going to talk to you about is going to be something familiar. Okay? Have you ever wondered why solids have a fixed shape? We always learn in science, solids have fixed shape, fixed volume. But have you ever wondered why? Why is it that the table is always solid? No matter how you touch it and how you break it, it will always be in a definite shape and a definite volume. Okay? Today we are going to discover more. Let me first of all bring out my very important tool, a magnifying glass. Okay? And from that we will look into the particles that is in front of us, and this is what it will look like. Okay? The particles in the solid are arranged like this. Now audience, my dear fellow audience, what can you tell me about this? About the arrangement of the particles? Any response? One of the pupils at the back. Okay? What can you tell me about the arrangement of the particles here? Okay? They are ordered, right? Okay? And they are all very closely packed. Very good. Okay? In a solid, all the particles are vibrating about a fixed position, and they are all closely packed together. That is why they have a fixed shape. But in liquids, things are slightly different. Okay? If you want to have particles and use the magnifying glass again and see the particles in liquids, you realize that they do not have a definite shape. This is why when you pour from container to another container, the particles and the liquids will take the shape of the container. Okay? And if you pour to another container again, they will change in height and also in the shape as well. Okay? Now how about gases? Gases have a very different thing. They do not have a definite volume. They do not have a definite shape. That is why when we look at a gas around us, they are all bouncing about. They are all moving about because they are not confined. And that is why gases do not have a definite shape. Let me sum this up. Why is it that solids have a fixed shape? It is generally because solids, the particles in the solids are arranged in a fixed shape, in a fixed order. They are vibrating about their position, and that gives it its fixed shape. In liquids, they are allowed some freedom. They have some free space to move about. It's slightly like during recess when the pupils are moving about in the canteen, but they're all contained inside the canteen. Okay? In gases, the particles are free to move about. It is like after school, when all the pupils are released and they just run all over the place. Thank you very much. I now invite questions from the audience. If you have any questions, please feel free to ask me.
Judges, any questions?
With the demonstration, you show that the molecules in water
Given the materials that was given to me, I thought of this because when I moved the particles from bottle to bottle, they were able to see the difference in height and also the difference in the shape of the container. Probably something better will be using green beans where it can really flow. It will give the concept of liquids much better.
Okay, thank you very much, Marcus. Just in case you're wondering what the secret ingredient was, it's actually 2 sheets of A3 size paper, 5 ping pong balls, and a set of cutlery which includes forks, knives, and spoons. Okay. Our very next contestant is Mr. Danny Aoyong from Victoria School. Danny?
Good afternoon, everyone, ladies and gentlemen. I'm Danny, and I will be doing a demonstration on a fun and simple science experiment which every one of you can do it at home. First, I would like to have a volunteer. Anyone would like to see a volunteer? How about come up from the front corner? Okay, thank you. You're very enthusiastic volunteer. Okay, first, may I know what is your name? Jerome. Okay, Jerome. Okay, in this science experiment, I'm going to need a funnel, which I made it myself. It's just a slip of post-it paper taped to a straw. Simple as this. You can try this at home. Okay, I'd like Jerome to hold straw. Okay, next. Now we need Jerome. Jerome is going to attempt to blow the ping pong ball out through the straw, and he's going to attempt to blow it out of the funnel. Okay? But before he does that, can I have a show of hands who thinks that he can blow the ball out of the funnel? Raise your hand if you think that Jerome can blow the ball out of the funnel. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. Now, who thinks Jerome cannot blow? Will not be able to blow it out? Okay, quite many hands. Okay, now let's see. Okay, now Jerome. Okay, on the count of 3. Okay, I want you to blow as hard as you can to get the ball out of the funnel. 1, 2, 3. Try again. You want to try one? Give it a best shot, come on. Okay, audience, let's thank Jerome, this is great for you. Okay, now let me explain what I've just shown. Okay, we have a diagram of the funnel. Now I'd like the audience to help me answer a few questions. Okay, now we're going to compare two regions. One region is the air in the straw. One region is the air above the ping pong ball. Now, noticing that Jerome blows the air through the straw. Okay, what do you think has happened to the air flowing in the straw? Did it move faster or did it move slower? Did it move faster or slower? Faster? Slower, anyone? Did the air move faster? Faster, very good. Okay? The air flows faster in the straw. Now, as compared to the air above the ping pong ball, the air flows much slower as compared to the air in the straw. Now, I'm going to bring you Bernoulli's. I'm going to introduce to you Bernoulli's principle. Okay, and you can read. It's quite difficult. Okay, so to simplify, I'm going to explain what it means that if there's a faster air moving, there will be a lower pressure. And likewise, if there's a slower moving air, there will be a higher pressure. So, okay, in relation to this, when Jerome blows the air through the straw, the air flows faster. So do you think the air pressure is lower or higher? Lower, very good, good answer. Air pressure is lower and the air pressure at top is higher. Okay, now we have one more. Air will flow from a region of high pressure to low pressure. So what happens? The air pressure here is higher, the air pressure here is lower. What happens then? The air rushes in to the funnel and as a result, the ball is pushed to the funnel. That's why Jerome is unable to throw the ball out of the funnel. Now, who wants to see magic? Anyone want to see magic? Okay, let me show you. Now, I'm going to put it in the inverted position. Now I'm going to blow it. Do you think will the ball drop or will the ball stay in the funnel? Stay. How many say stay? Wow, most of you have been listening. Okay. Sorry. Okay.
Thank you very much, Danny. The floor is now open for any questions.
Now I want to blow the ball out. Okay, how do I blow the ball out? Okay, as I said, Bernoulli's principle acts on pressure and velocity. What you do is to, the trick is to go across such that the ball will lift up. Can you demonstrate? Okay? Any more questions? Yes?
Can you explain what's the difference between this and an air rifle gun?
An air rifle gun.
So you can shoot.
Air rifle gun. Okay, this is uses the difference in velocity to give you a difference in pressure to give you the force. Whereas air rifle gun is just compressed air. Compressed air. And the use of compressed air to propel the pellet. Thank you. I hope, thank you for being such wonderful audience, and I hope you have learned something new today. Thank you.
Thank you once again, Danny. Our next contestant is from Ahmad Ibrahim Secondary. We have Mr. Kong Cheng Shik.
Very good afternoon to everybody here. My name is Cheng Shek and I teach in Ahmad Ibrahim Secondary School. And I've got a really interesting experiment to show all of you here today. I've got found finally good use of this encyclopedia my dad bought me 10 years ago. So yellow. It's really good. And paper experiments, we can do many of these. And I would like to share more about making sense, physical sense of numbers. Physical sense of numbers and measurements. Now, I'm sure many of us have encountered questions like this before. How am I going to support this book with paper? And all of us will say, let's roll it up. Right? Roll it up and we can support it. So why don't we just roll it up now? And let's see if it really can support this weight. No, but the thing is not about telling us how it can support paper, the weight, but more it should be why. Why a rolled up paper can support the weight. I'll give you a minute here. A bit nervous. Yeah. My wife doesn't know I came for this competition. Yeah. Because she didn't know the first prize is San Francisco. And I've got an 8-month-old baby. He made me stay up all night. And I want to get away. I thought it was a good time. So will this be able to hold this? Well, let's see. Let's have a look. I'll balance it properly. And yes, you can. Wonderful. Now, before we go on this experiment, I'd like to ask 2 volunteers from the audience and to stand up and just answer those simple questions about the wonderful man there in yellow shirt. Would you mind stand up, please? Thank you very much. Yes, and let's have another young man here. Oh, let's stand there. And how about the man there with the sexy mustache? You don't have to cover the mustache. Yes. The man in the striped shirt. There's a really wonderful looking mustache. Yes, thank you very much. Yes, I've got a question to ask you, and it might take some time to recall. Are you able to touch your toes?
Yeah.
Sure. Is it easy? Okay, how about you? Yeah, no problem. Oh, that's very good. That's very good. Now, thank you very much. Yes. Now, we'll come back to that later. Anyway, what's your name anyway?
Dave.
Jack.
Dave.
Jack. Yeah. For this experiment, you're Jack. Yourself, you are? You're Jill. We'll confirm that with your boyfriend later. Now, how about this? What's the difference between they're the same height? Let's load this even more, huh? Load it a bit more. It's okay? Right? Let's try this fella. What we will take it? I don't know. First, I must be able to balance this thing, which is a bit difficult. And it's wobbly. And then I balance this again. And see if you can. It's giving way because it's tilting, and if I do a bit more, it actually compresses under the load. And the entire thing, entire structure will start to bend. You see that happening? Now, what is the difference? Why this can hold the load, this can't? Same height, different thickness. And that's the property that allows it to hold the load. So how do we make this hold the load? That's right now, it is a different story. At the end of today, I would like you to take back with you this thing. We know that the longer the thing is easier to bend, the wider it is, the more difficult it is to bend. So let me introduce to you this little ratio of measurement which gives physical interpretation, which I call elbow bar. This is called a slenderness ratio. An object that is not slender, that has a high slenderness ratio, will be able to bend easier. And that otherwise will not be able to bend that easily. Thank you very much.
We can take some questions now.
Yes. Oh, Jack and Jill is tucking the toes. I think we'll leave it to them to demonstrate the sit and reach for us, shall we? Would you like to demonstrate the sit and reach for us to see if it's easier to bend? No, it has nothing to do with Jack and Jill at all. It's just that, take me for example, alright? Alright? On the side view, I'm the same height, but I've got this little, thickness here. It's easy to, but on this side, it's really difficult to bend. It's difficult to bend. So the slenderness ratio tells us how much load can we apply onto an object before it compresses, it bends, and it fits. Yes. Yes, thank you.
Explain why you say demonstration is not physical sense of numbers, measurements, not statics or something like that.
Can I answer? Alright, the slenderness ratio, every material, paper, metal, have a slenderness ratio. And that slenderness ratio relates to the amount of moments it can take before it breaks, it bends and collapses. That is used in architectural designs, building designs.
Okay, thank you very much. Our next contestant is Mr. Fong Lei Lian from NUS High. Oh, Miss, I'm so sorry.
Hey, good afternoon, everybody. I chose paper because, it's most versatile and it's like the thing that is something I would actually write experience. And today I'll be talking about vibrations and sound because I thought I'll be nervous and my hands will be shaking. It will be vibrating, so it'll be just nice. First and foremost, perhaps if you could feel what causes sound and frequencies and vibrations. What I have here is actually sheets of paper. If you could take like 2 each, right? This is 2 each. I'll take this one. 2 each and pass it on. Okay? Yeah. Well, to feel the vibration, if you were to put both here. This used to be a childhood game. You take 2 leaves and you put them together and you blow. And if you put it here, you can actually feel the vibrations against your lips. Yes? No? Aha! Yeah, I hear something. Right, do you feel it? Do you feel it again? What was it that you felt? Thickness, vibrating, and if you blew harder or you blew softer or you gave it a little bit tighter, you made it a little bit soft, what happens to the sound? Against the lips. what's the word I should use? That's right, amplify. So I'm using the paper to amplify the sound. What's happening here? What's happening? The vibration goes from the rubber band to the paper, and that vibrates in the paper, and we already knew that the vibration is the source of the sound. Okay. So I'm just using this as an amplifier. Thanks for the words. Okay, actually my demo is more or less done. Except I've got this wonderful piece of plastic. This piece of plastic actually has got striations. That means got marks that scored in it. And as I run my nail across it, it actually creates sound. But I'm hoping to be able to amplify that so that you can hear it. I'm just taking a position here. Right, you can hear it, but it's not very.
For the first demonstration, how would you make vibrations here in the crowd?
And probably how tight you should do this. If you measure in guitar string, if you don't have a guitar, then you see the guitar like this. And varying the tension of the rubber band to come in. Okay. Thank you very much.
Our next contestant is Jerome Liao from NIE.
Alright, good day ladies and gentlemen. Now this 5 minutes presentation is dedicated to all those lonely out there and to all those who make New Year resolution to make new friends, to find new partners. This 5 minutes presentation, it will be worthwhile. You have no waste of trip down to Science Center here. Now my demonstration today is not gender biased, whether you are male or female here. It's still applicable to you. So sit back and relax. Let's get started here. So it's New Year 2006 here. You are invited to friends' New Year party. So all get up, hair gel, new shirt, new pants. But don't forget to bring your balls, your ping pong balls here. Alright? So your purpose there is arouse interest, right? So when you walk to the birthday, walk to your friend's party, new party bash, your friend will ask you, hey Jerome, what's that inside? Yeah, you say, these are my balls. Alright? So the new friends here, you saw a lady and it's your dream girl. Your heart starts beating faster and faster. Hey, I want to know this girl, this lady down here. And this lady down here was drinking can. Line the code here. And you say, and you walk over to the inside, you say, hey, my name is Jerome. And you take out first ball. Now can you believe that I can actually blow right through the can and the ball will still move? And the lady said, wow, you can do that really? And I said, yeah, of course I can. Then a few magical words say, abracadabra to the magical ball, and here you go. You see that? You see that? I can blow straight right across the can, through the can. And she said, oh, why? Why does it happen? And you're not going to stop there, right? You're not going to stop there. You're going to press her further. So with just another demonstration, you're going to grab another hairdryer from your friend's house. Alright, you cannot find a hairdryer, never mind. I will show you how to use a straw later. Alright, so grab a hairdryer, grab one, and you say, hey, this is not a trick. I can levitate this ball with just a hairdryer. And say, oh, is that interesting? Alright, so you just hairdryer, move glass, to levitate the ball. Alright, this is the moment now, guys, ladies and gentlemen. Now let her touch the hairdryer now. Now you're going to turn to hold her hand. Hold her hand now. So this is not Harry Potter's magic. This is what we call Bernoulli's principle. It's found by the Swiss scientists in 18th century. Alright? And this Bernoulli's principle is surprisingly that, when the speed of the fluid can be gas, can be liquid, it's very high, the pressure is very low. And the speed of the fluid is very low, the pressure is very high. This kind of seesaw thing. So now in this case, the can here, when I blow, the air is flowing, steady flow, very high speed, low pressure region, atmospheric pressure, to push the ball. So it flows this way, it goes this way. Same thing for your hair dryer. For the hair dryer, strong gush of air, steady flow. Alright, so this region here is low pressure region. Atmospheric pressure will keep the ball in place. Isn't that nice? Isn't that neat? Alright? Now, ladies and gentlemen, it does not take money to make new friends. It doesn't take a can of Tiger beer to make new friends. All it takes is just physics. It's just your balls. If you 3 not enough, have 5. 5 not enough, have 10. Have more balls if you have the courage to make new friends there. I'm going to tell you a secret, ladies and gentlemen, here. Because you know physics, and because you know Daniel Bernoulli here, you're going to conquer more land, more territory. You're going to make new friends, more new friends here. So, good luck, ladies and gentlemen. Physics. Thank you.
Thank you very much, Jerome. We take some questions for Jerome now.
Oh yeah, I forgot the straw. I'm so sorry. Okay, the straw is, just cut the straw into 3 parts here. Now place your ball inside these 3 parts. Alright, if you don't have the scissors, it's not the end of the world. Alright? You can still demonstrate without the scissors. Who says you can't do it?
Okay, thank you very much, Jerome, for those neat tricks. And our next contestant is Miss Lim I Ping from Millennia Institute.
We will die in shame or die in glory together. Okay, now, my name is Lim I Ping. I'm from Millennia Institute. Hi. Well, Jerome is a very tough act to follow. Okay, we'll try. Okay, try. Alright, sorry, I was a bit worried about audience reaction, but I shouldn't be. I was trying to do my demo myself, so that I don't when I ask for volunteer, that's it, I'm faced with a dead silence. Okay, never mind. Okay, actually I've planted someone to help me, but I think I'll do it. Now, actually, it's a very simple principle. You can do it at home. If you want, you can actually try it now. Basically, what you just need is a piece of paper. Parents, this is very good for teaching your kids. You just need 1 piece of paper. So all you do is, I think you can guess what's coming. I'm going to make the paper rise. Now, I'm not Harry Potter. I don't know magic, but I'm a physics teacher. Alright? So by rolling across, what do you think will happen? What do you think will happen? The paper will rise, right? Okay, cannot lock it. Can I see? No. Oh, thank you. Oh, very good. Thank you. You see, it's okay if I blow here, of course it will fly up. But why is it when I blow across the top, it will fly up? After all the physics lesson just now, come on. Why is it when I blow across the top, my paper go up? Can you remember the name? Previously, 2 teachers already taught you all. Cannot shame them. Quick. Starts with a B, verb. Bernoulli is a verb. Very good. You are very good audience. Alright. Now, Bernoulli is a verb. Yes. They already explained it for me, so my 5 minutes is much shorter. Thank you very much. Thank you. Alright. What you do is when you blow, the air across the paper is obviously moving faster. So they say when the air is moving faster, what happens? The pressure is actually lower. Yes, the pressure is lower. And below, there's no air moving, so the pressure is higher, that's why the paper lifts up. Now, simple version. Next time you go out, you want to impress, not impress, but you want to make fun of a friend. Then you say, okay, who can roll the paper apart? Then you take out this roll of paper. This is a way to get to know girls too, alright? You just say this, then you know you got a rival there, so you want to impress this girl, then you challenge the rival. You can roll this paper apart now. Then when the rival try to blow, what do you think will happen? When I blow, the air in between the paper is going to be moving. Yes. And the paper at the side, the air at the side, not moving, right? So what will happen to the paper? Will the paper move apart? No, they move closer, right? Okay. Try. Basic. And this is why, ladies and gentlemen, when you take the MRT, they say, train is approaching. Please step behind the yellow line. Can you imagine you're standing here, the train is coming, the air is moving along, and then you're here. You will feel this irresistible force pushing you towards the MRT. So always stand behind the yellow line. Okay? Thank you.
Thank you very much, Ms. Jing. We can take some questions.
Actually, you all have asked all the previous one, so I don't need to. Why is the air moving with the train? Actually, our first contestant, Marcus, had mentioned something similar. Friction. He said, why does things have friction? The MRT surface actually is rough, comparatively rough, and air molecules, friction, move together. How to say? It's cohesive. It will move together with the train because of friction. Let me just show you, it's easier. Wait, I want to make this thing move. Right, this is a surface, this is a surface. Think of this as an air. Think of this as an air. I want to make it move, right? I need to exert a force, right? I need to push, then you move, right? Otherwise, by right, you wouldn't, right? Let's say this is a moving MRT station, When the MRT moves, what happens to the air? When the MRT moves, what happens to the air? It moves with the MRT. Agreed? So the layer closest to the MRT tends to move together with the MRT. Then layer further away, of course, not so much. Is this clear? Can I understand? Cannot, I can explain more. Okay. Alright? Okay. Thank you.
Our next contestant is actually Mr. Lim Jin Mia, but I'm not too sure if he's here. No? Okay. Okay, so we will go on to our contestant number 8, which is Miss Lim Hui Chin from Meridian JC.
Okay, ladies and gentlemen, a very good afternoon to all of you. Okay, before I begin, I would like to invite a strong, healthy young gentleman to help me with my demonstration. Maybe this gentleman would like to help me? Okay. What's your name, please? Yang Yue. Okay, what am I going to ask Yang Yue to do? Okay, basically, I'm going to ask Yang Yue to hold this piece of paper at his mouth. Okay, and before he begins his task, perhaps you can make a prediction. I'd like you to make a prediction. Okay, if he blows the paper over the top, what do you think will happen to the paper? Okay, because it blows across the top, is it logical that the paper will just move downwards? Because it blows it away. Or would you expect the paper to levitate? Look at intelligent guess. How many of you guess it's 1? The paper will be blown down because Yang Yue pushes it down. How many of you think that, it will move up instead? Okay, thank you. Yang Yue, please demonstrate. Not touching, just in front, and blow across the top. Maybe you think this piece of paper is too small. Never mind. Let's try a bigger piece of paper. Blow and touch. Let's simulate, okay? hold it close. Forward. Okay. Wow. Okay, let's give him some encouragement. Okay, thank you, Yang Ye. Why is it that the paper defies gravity and even defy all our expectations of what will happen to the paper? To understand this concept, we must first understand fluids. Okay? When we talk about fluids, we think about liquid correction fluid, cleaning fluid, lighter fluid. Must fluids be a liquid? Do you think it must necessarily be a liquid? Not necessarily. The word fluid has its root in the word flow. Okay? And flow, besides liquids, what else flow? Gases also. Okay? So am I right to say that we are all swimming in some fluid here? What is the name of that fluid? Air. Okay? So in the 18th century, the scientist by the name of Daniel Bernoulli discovered a certain effect on the fluid, which we now call the Bernoulli effect. He says that, okay, in a room in a continuous fluid, okay, the velocity of the fluid, where the velocity of the fluid increases, the pressure, the internal pressure of that fluid decreases. This relation, okay, is it a direct proportion? Is it a square? Okay, by the law of conservation of energy, he derived that, okay, the relation is such. That this term here, rho is density, v is velocity, and p is pressure. So at any point in space, okay, where the velocity increases, the pressure will decrease. So if we consider the piece of paper, and you blow across the paper, suppose the air below is, okay, not moving, it is at atmospheric pressure. But because Yang Ye blows across the top, okay, when he blows across the top, the velocity increases, and therefore the pressure here decreases, less than atmospheric pressure. And we know from secondary school that, okay, the pressure equalizes, and as the air moves from high pressure to low pressure, okay, it lifts the paper with it. Thank you.
We can now take some questions for Ms. Lim.
Science paper usually affect best why? Science paper will affect best why?
Lightweight paper, because what pushes the paper up, what lifts the paper up is actually the pressure difference. Size. Small piece of paper that is not too stiff. Because if it's too big, the weight is too large. Yeah. Okay, our next contestant is Miss Lim Lek Lee from Kranji Secondary.
Okay, so previously one of the gentlemen actually has shown you how to balance the book on the poster. Alright? So he can do it actually partly because he knows where the center of gravity of the book. Alright? Okay, so for today, okay, I just want to show you if it's a non-uniform object. Okay, so how are you going to find the center of gravity using two fingers? Okay, so I would like to invite the volunteers, okay, from the audience so that you can try it on your own. Okay, maybe we can invite Mr. Malik to come down. Alright. Okay, Mr. Malik, I want you to put the two fingers at the side. Okay. Alright, okay. And I want you to move. Okay, that's my challenge. You have to move both at the same time.
Both fingers at the same time.
Yeah, that's right. What do you notice?
My right finger will move first.
Okay, so you notice that the right finger moves first. Okay, but what, can you move this now? Alright, okay, now the left will go down. Okay, so continue. Continue. And where do you stop? Alright, so what do you notice? Can you balance? I mean, do a bit of shaking. Alright, okay, so you can actually balance the chopsticks here. So you know that the balance point, the center of gravity is here, okay, and then the fingers is actually directly below the center of gravity. Alright, okay, now, another challenge, okay, okay, maybe I just want you to find out what is the difference. If you put at the same distance from this center of gravity, okay, I already marked the points there, so you just put your fingers there. Okay, alright, now you start to move. Any difference from the previous case? Do you find it a bit easier to move both hands at the same time? Okay, let's put it here then. Okay. I mean, the difference will not be that great as compared to the previous case. Alright, okay, so what is the reason here? Okay, what is the reason here is because, okay, thank you, Mr. Malik. Okay, thanks. Okay, it's actually because of the frictional force involved in this. Alright, so this is the place that, this is actually the center of gravity. Okay, so if you put your fingers around here, okay, if you are closer to the center of gravity, that means the weight that it needs to support is greater. Okay, and the reaction force is here will be much greater. Okay, so and you find it a bit more difficult for you to move. Okay, but when you look closer to it, then you find it is easier now. Okay, and friction, because friction is actually directly proportional to the reaction force there. Okay, alright. Okay, so what happens if you attach the weight or a mass at the side, okay, and you notice that the center of gravity will now be different. Alright, okay, so it will be more towards the one that has a greater mass. Okay, and you can use this in different toys. Okay, some toys that you found in the market where you can actually balance it. Okay, you can balance it. Okay, and I'll try to balance it on this. Okay, hopefully it can work. Okay. Okay, my hand is really shaky. Okay. Alright. Okay, so it's actually balancing on the top here. Right? Okay. And what's the reason? Because the center of gravity is actually directly below the pivot. Okay, thank you.
Questions?
For the chopstick demo, initially it places both fingers exactly the same distance and the same reaction force. How does it start contributing?
Okay, we place it at the same distance. Okay, so one of them will move a bit faster because okay, so the topic that by right it should be moving at the same time. Okay, but the friction that we produce might not be.
Okay, thank you very much. Okay, our next contestant is Mr. Lam Chi Peng from Pioneer Junior College.
Hello everybody, the star of the show is Bernoulli, right? You can see, so I composed a tune specially for this chap. This for you, wherever you are, Bernoulli. Thank you for great science. Okay? Now, it's easy for because everybody has said everything, so I just go on. Bernoulli, that's how it's spelled. Okay, can see or not? Now, Bernoulli, you know, is simple. Okay, fluid now apply to air. From a demo of air. Air speed high. Okay, pressure low. Air speed low. Pressure high. You have song. High, low, high, low. Okay, so simple. Just remember air speed high, pressure low. And air speed low, pressure high. That's it. Okay? Now, demo is nothing very much. I think it's new. Just that I want to go further. You've seen this, but why is it like that? Okay? You don't know why, right? Okay. Bottom, high pressure, obviously, right? Low speed, why? Higher pressure, low speed, why? Anyone? Surprises, huh? Because of what? Because of F. The air touches the ball and there's a FR. Friction. Yeah, friction, correct, thanks. Surprise. Yeah, friction. So you know why, right? You'll find that there is a lower speed gauge, as you know why. Okay? Now, soccer time, so I go on to soccer now. I can't use soccer ball, okay? So we'll use ping pong, so I use ping pong. Now, when I'm playing the ping pong ball, I learn one trick, that's all I know. I lose every game, but I have one trick, it's called top spin. I hit the top, the ball spins, spin this way, going down. And because of spin, you will dip across the net, okay? Right? Because I'm lousy check, it dip, but then you go outside the ball. But it's a dip, so it's supposed to surprise people, right? So something like this. You don't hit this way, you hit a side dip. You see a very dramatic dip. Now, if it's a soccer ball, it's the same thing. The World Cup now. Ronaldinho, the finals, okay? You kick the ball using this style, okay? When you spin this way, the airflow will be opposite to the spin on top, right? So what happens is that you shot the ball, it's as if going over the goalpost. And lo and behold, when the goalkeeper was, never mind, it's okay, going over, suddenly the ball dipped down. So at the corner, gone, okay? One down, okay, for the opponent. Okay? So you see a lot of Bernoulli effect in soccer. And Beckham's banana kick, right? See, the ball spin this way, so the ball spin this way, goalpost, that spin. They spin, 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 and go! That's it, the corner, again. So you see a lot of Bernoulli effect in soccer. In tennis too, I can't do it, but my friends can do it. Top spin, go across the net suddenly, and then the opponent doesn't know. In volleyball, super takraw, question, in Tiger Woods, golf, it's different. It's a bottom spin, why? Why? Bottom spin. Spin to the bottom, why is it so? Anyone? What's the aim of golf? You want to go what? Go up, right? The force is up so they can stay longer and lo and behold, all in one, right? And then up. So it's different. The top spin, bottom spin, the side spin, all depends on your ball game. Like that. So another one, the prizes. One more question. Now, I think you have seen it, I think you know. It's opposite what you think. If I blow the thing, the ball would come together, touch. Now, instead of going far apart. Why? When you blow, the air, something happens. So what's the reason? The speed will become what? Faster, the pressure lower. There you are. There's a compression effect. Is it again? So you can see Bernoulli effects everywhere. And Ms. Lim said that she wanted to do a aerofoil. Then I do it for her. Aeroplane, okay? Aeroplane. You can fly. You can fly. Okay? Why? It's because the air is the wing is built such a way that it's longer here. Let's say you and girlfriend go, it comes here, so it's faster here, lower pressure. Down there, higher pressure. That's the Bernoulli effect. Okay? There's any question? Can I ask a question? Question time, right? Can I ask process question? Reverse questioning. I was thinking of this capo, I can't understand. Okay? Why is it that when I spin the top? Sorry. When I spin the top, the top's supposed to spin, yet it doesn't topple. You know, I'm not sure. Seriously, I'm not sure. Can you explain this? You can ask question like that. I don't know. Yeah, but I don't know why. It's supposed to be spinning. Okay. I don't know why that topple is don't effect. Why the top? I'm puzzled. I'm curious, skateboard. You know. I don't know why. Honestly, I'm not sure. Yeah, answer that. Okay, never mind. Any questions? Yeah. For example, okay. I think the example I can think of sailing. I love sailing. Okay. I'm down here. I was sailing to the stick. Okay. Let's go sailing. The wind is coming here. Then I'm in trouble, right? The wind's opposite of me. How can I sail there? So the sailor used Bernoulli effect. They turn the boat here, go here using the wind. The sails there. There you are. The sails here. I know details, but that's the fact that you can use Bernoulli effect. Okay? Therefore, go opposite the wind direction. Okay? Beautiful. Thank you, Bernoulli. All the best to you.
Alright, thank you very much, Mr. La. Okay, so we will move on to Miss Osman Faiza from Bedok North Secondary.
Hi, very good afternoon to everyone. Yeah, it's another presentation on our good old Bernoulli. Now, how many of you here, before I start, can I have a show of hands? How many of you here have actually experienced this? You are standing by the roadside or at the road divider, waiting to cross the road, when suddenly you see this huge army truck or some other huge vehicle that's moving at really, really high speeds, and as it's passing you, somehow you experience this feeling of being pushed into the path of this heavy vehicle. How many of you have experienced that suction sensation? Yeah. Some of you have, some of you have not. For those of you who have, I think you were able to resist that push, right? Otherwise, you wouldn't be here today, okay? Yeah, so let me demonstrate to you this particular demo. And okay, I believe many of you have seen this before, especially in the shopping malls on the larger scale, am I right? But instead of using a ping pong ball, a beach ball that's more colorful is used, and instead of a hairdryer to provide the moving air, a large motorized fan or the end of the exhaust pipe is used, alright? So I know some of you would have actually placed your hands above the beach ball to check whether there's actually a string that is attached to the beach ball and is supported by the ceiling. Well, much to your amazement, or horror should I say, you realize that, well, there are no strings attached. So by what strange magic, okay, is the ball being able to suspend freely within the region of the air? So that's where a principle comes in, and that's the Bernoulli's principle. Bernoulli's principle can be used to explain the earlier case with regards to the fast-moving heavy vehicle, or this particular case, the demonstration shown. So Bernoulli's principle, simply stated, okay, let's make things easier. It just states that in a region, okay, whereby the fluid, which can be a gas or a liquid, moves very quickly, the pressure in the fluid, okay, would decrease. And the opposite is true. When the fluid is moving very, very slowly, the pressure within the fluid would increase. So let us apply Bernoulli's principle to the demonstration that you have just seen just now. So what I have here is this symbolizes, the two lines here symbolizes the flow rate, okay, the fast-moving air, okay, this is the fast-moving air coming from, of course, the hairdryer. Now, we are surrounded by the air in the auditorium. I would say that relatively it's not moving, okay, compared to the fast-moving air. So we say this is still air, okay, still air. So by applying Bernoulli's principle, we state that when the fluid is moving at very, very high speeds, okay, we can say that the region, the pressure in this region would be low. Okay, that's applying Bernoulli's principle. And for still air, okay, not moving or moving also very slowly, we say that this is a region of high pressure. So likewise here as well, we have another high pressure region that is surrounding, okay, the ping pong ball. So high pressure region here. Now, so what happens is, the reason why this ping pong ball is able to float very nicely there is because, for example, should it wish to leave the low pressure region, okay, approaching the boundary, due to the pressure difference here between the high pressure and the low pressure region, there will be a force. And this force is directed from a region of higher pressure to a region of lower pressure. Likewise, should this try to leave on the other side, okay, there will be a pressure directed again from the region of high pressure to the region of low pressure. So, of course, this is in 2D. If we take it from a 3D point of view, from all 360-degree sides, okay, there will be forces directed from the region of higher pressure, which is the surrounding air, atmospheric air we are in, to the region of lower pressure, which is the region of the fast-moving air. So that is Bernoulli's principle being used to explain the demonstration that you observed just now. So basically Bernoulli's principle, with that knowledge, we are able to apply it to practically quite a lot of applications that you are seeing around us. So I thank you for your kind attention.
Thank you very much. We can take some questions.
How is the ball? That's because of the air that is being blown. But the thing is, the question is, why doesn't it leave, or come into or come out from the area of the blown air? Yeah, why is it still within that area? So it's because of Bernoulli's, the fact that there are forces from the region of higher pressure acting on the ball, preventing it from coming out from the lower region area. Yeah. Yes, the weight plays a part. Of course, when I tilt, if I tilt the hair dryer, of course the weight comes into the picture, and it will be too heavy to support. Yeah.
All right, thank you very much, Ms. Aida. Right, so we have Mr. Yu Hui from Damai Secondary.
Okay, just as a side note, actually today is the O-level physics paper actually. Yeah. So the students are actually taking their physics paper now. Okay, so for today, right, what we're going through is something to do with eating utensils. Okay? So one of the secret ingredients is a set of eating utensils, both Chinese and Western. So obviously I don't have enough time to bring a fishball and all that, okay? But you just have to use your own imagination. Yeah. So okay, let's say we have a fishball here. Right? So you have a fishball. Of course, we know that the correct way to use a pair of chopsticks is to grip it this way, the chopsticks will crush, and just pick out your fishball and so on. Okay, but for one of the younger kids, right, then of course they always prefer not to do that. Then they will always take the chopstick and they spear the fishball. Yeah. Okay, so if you just imagine this magical here is the fishball, right? You notice that it's actually quite difficult to use the chopstick to spear the fishball. In fact, of course, you as a parent, you always tell the kids, don't play with the chopstick, use a fork. Then you use a fork, you find it's easier to spear. Yeah. So with the same force. So actually, what is at work here? What is at work here is actually very easy. It's actually the pressure. Okay? Your chopstick, the end, right, is actually quite big. So it's a big area. Whereas your fork, it actually has a small area. So the pressure, right, is actually the force over the area. And when there's a big pressure acting on the surface of food, right, then what happens is that the local area there will actually deform and the food will tear, and then the fork will actually poke inside. And hence you get your big revolt. Yeah. Okay, then of course we all know that in Chinese cooking, nobody has a stick, one whole piece, because it's very difficult to use chopstick. I mean, Chinese cooking always chop out into small pieces of meat, then you stir fry. Of course, Western, they have one giant piece of stick there. So what are you expected to do? You're supposed to take a knife and you just saw the thing, and then you're supposed to eat it. Okay, so, okay, why is it that the knife can actually cut? We can't use the chopstick, right? We can't say use the chopstick to cut the steak. No, cannot. Right? So why is it the knife can cut? It's also very simple. If you look at the side view of a knife, right? Okay, this is your knife, right? Okay. But if you look at the front or your front view or side view, right? Actually, again, you got a small area. Right? This bottom part, this entire part here is actually the area in contact. So it's the same thing. When the area is very small, then the pressure will be very big, and the local area will actually be small, and the food will tap. Okay, then I ask you, if let's say the plastic knife, right, not sharp enough, because dangerous, right, not very sharp. You notice that they put this saw edge, serrated edge they call it. So, how do you think the serrated edge helps? Again, it's the same thing. You put your foot inside. As you press down, right, this part here, as you press down, where the saw edges jut out, right, the pressure will be actually higher. So this pressure is higher, the foot more likely to tap. And there, right, one thing, when you do a dragging motion this way, then it's more likely to drag the foot along and tear it. So make it a lot easier. Yeah, so that's the physics of the eating utensils.
Thank you very much. We can take some questions. Yes, we have a question over here.
So, carbon knives are always serrated. Right. So why is it versus a carbon knife and a very sharp knife with the same
Okay, it makes it easier because it's not only the downward pressure that actually deforms the meat and what. When you have the serrated, right, these portions here more likely to penetrate. Plus the sideways motion, you actually drag the meat along. So when you have dragging motion, it's more likely to tear. So you can actually cut with that small. Yeah. The concept of saw basically.
So we just take one more question.
If you can generate the necessary pressure to deform and break the meat, yeah, if the force is big enough. Of course, the serrated edge will actually help you.
Thank you very much. Okay, our next contestant is Mrs. Anita Prasad from TBS International.
As you all have given only 5 minutes. So here, V1F and V2F are the final velocities. M1 and M2 are the respective masses. And V1I is the initial velocities and V2I is the initial velocity for the first ball and V2I is the initial velocity for the second ball. Similarly, for the final velocity for the second ball is given by this derivation. Now, as we saw, when M1 is equal to M2, right, and V2I was at rest, right, so V2F took the initial velocity of V1I. Is that clear? From this, we substitute these values in this equation. Similarly, say M2 is very large, say this table. And M2 is at rest. And this is, if I drop this with say velocity V1I, what will happen? If I drop this, it will bounce back in the reverse direction. That is called my V1F will be equal to the minus V1I. Okay? So when M1 is equal to M2, V2I is 0, V2F is V1I and V1F is 0. Now this knowledge is also used in the nuclear reaction also for slowing down the neutrons. Thank you very much.
Thank you very much. Can we take some questions?
Sorry. This is a mass, another body, and this was the first body, second body. So there are no collision forces between them. So this is considered as a very massive than this ball. So when there was a collision, there was a bouncing back. So V1F was found is equal to the minus of V1I, that is in the next.
Your equation neglects the rolling of the ball in your demonstration because it rolls. How does that affect your result?
This will come in a 2-dimensional, 3-dimensional motion, which I didn't. I have restricted my explanation only to the 1 dimension.
Does it explain why your ball jumps?
No.
Okay, thank you very much. Our next contestant is Mr. Sufahat Malik from Kranji Secondary.
Hi. Okay, hi everyone. I'm Malik from Kranji Secondary School. Okay, I'm here to demonstrate to you concept of physics using a simple, using an ordinary ping pong ball. Okay. Okay, let's begin. So here I have a bottle full of water and a ping pong ball. As you know, when I place this ping pong ball inside here, it floats. Now, why does it float? Now, it floats because, as you can see, it doesn't move, right? It doesn't move. That means there is no unbalanced force. There's a force upward, and there's a force downward. Sorry, upward, and there's a force downward. Okay, and this force must have been equal, or not you wouldn't have moved, right? Alright, so it must be equal. Now, this downward force is obviously gravitational force, which we normally call weight. That's what is W. And then there's upward force, and that upward force must be due to the water. Alright, the water must have pushed it up. Now, we call this force the upthrust. Let's call it U. So now, when U and W are equal, it will float. Oh, okay, now, let's take some other method. You have a $1 coin. As you can see, when I put in the water, it will sink. Now, why is it so? Now it moves. It falls down. Now, because obviously there's an unbalanced force, that's why it moves down. And the unbalanced force, in this case, W, it's still an upthrust force. But in this case, it's smaller than the W. So now we have a situation whereby the weight is greater than the upthrust, and therefore it moves down. In other words, it sinks. Okay? Now, question. Now, let me pose you one question. How can I make this ping pong ball sink? You understand this concept, right? Now let's apply this concept to see how we can make this ping pong ball sink. One instinctively, you might say poke a hole, right? So I have a nail here. So let's use another ping pong ball so that we can compare. Okay, let's poke a hole here. Okay, here you are. I got a hole, right? See? No joke, no kidding, Seriously, I got a hole, Okay, so. Alright, now I'm going to put on the water. As you can see, what happened? It still floats. No water goes in, right? Okay, you think maybe I push in. Maybe the water will go in. The hole still here. I'm going to push it in. What do you think? It will still float? Yes, obviously. And you can see there's still no water inside. That means water did not go in. Crush. Wait now, we come to that one. I'll leave it to the last. We'll see what happens when it crushed, because I got 5 minutes on it. All right. Okay, now. So in this situation now, let's draw it. Well, let me draw you. Okay. Now I have a hole here, right? Now there's water here. Now why is it now the water doesn't want to go in? Obvious, right? Because there is air. Right? So there is air inside here. And what does this demonstration demonstrate? It demonstrates that air occupies space. And air has occupied space. Occupied space. So what? So why the water don't want to go into the space? And why the air is prevent the water from coming in? Because the air also exerts pressure, right? So air has pressure. So air pushes the water, prevent the water from coming in. Right? So water doesn't come in, so it cannot sink. Still doesn't answer my first question, right? How to make this ping pong ball sink? Okay, how to make this ping pong ball sink? What do we need to do? Poke another hole. Okay, let's try and poke another hole. Okay, so I have one hole here, right? Let's poke another hole next to it. Okay, now I got 2 holes. Make it more dramatic. 3 holes. Okay, right? 4 holes. Okay, now what happened? Let's see. So I haven't tried it. Still no water. Still floating. So what do you suggest? Poke hole, 1 below, 1 on top, right? There's a logical explanation. There's a logical thing to what is? Okay, now. So you see what happened? As you can see, slowly it's going deeper and deeper. Look closely. It's going deeper and deeper. Now counter, right? Okay, so you can let me be faster. Okay, let me explain. Now you obviously now the water pressure the water pressure now pushes the air up. Okay, now the water will start, if you look closely, the water will start to fill up. Right, and you can see that it's getting lower and lower. But still floating, still floating. Because this is still smooth. Now what has happened in this situation is, as water go in, the weight of the ping pong ball together with the water increases, right? So it should go down, right? But the updraft also increased by equal amount. So as a result, they are still equal phase flow. But look at it now. Now it really falls down. Now because this one is greater. Sorry, the weight is not greater than the updraft. So therefore it's moved downwards. Okay, thank you. Okay. You want to see? Everyone want to see? Yeah. Okay. What I want to show you is this. the ping pong ball and sink. Okay, now watch what happened. There's water inside, right? That's why you must have seen, right? But the water doesn't come out, right? Okay, but the water will come out on my command. Really? Okay, ping pong ball, please release the water. Ping pong ball, stop. Ping pong ball, release. Stop. Right. If you watch my fingers carefully, you don't watch what happened, Okay? That's very obvious lah. Okay, this one demonstrates what? I think you know lah. Right, thank you.
Our next contestant is Mr. Tan Hyok Chuan from Mahabodhi.
B-I-E, C-D-E, C-D-E to A-Y-E, A-Y-E, B-K-E, B-K-E back to N-I-E, N-I-E went to Mahabodhi, number 10, Ubi. I datang sini, very happy to do magic, but show physics, I teach mathematics.
Today Rosie is not around, but never mind, I'll show you some magic. Sorry, no Bodhini, just simple paper and an empty box. No magic. See, there's nothing. But sit carefully. Nothing on my head, nothing on my hand, nothing here, nothing there. But hey, do I see something? Simple magic. I have this piece of paper telling me about gravity. Someone, an Italian scientist by the name of Galileo, said that if you drop a ball made of metal, and you drop a ball made of paper, and you drop another ball made of styrofoam, 3 balls drop at the same time, which one will reach the ground first? How many of you say A, the metal ball? How many of you say B, the styrofoam ball? How many of you say C, the paper ball? So sorry, none of the above. It's number 4. All at the same time. So what little magic am I going to show today? I have with me here a piece of paper, plain paper. And what I'm going to do is I'm going to crush it and put it into this box. And ta-da-da-dum! I get this thing! That's magic! Thank you! Thank you, thank you, thank you! And what am I going to show you? These 2 pieces of paper are of the same size, same area, same type of glossy paper. But Galileo said that if the 3 balls are of the same shape and same size and you drop them from the same place, they are supposed to reach the ground at the same time. Magic always defy what is the truth, isn't it? So what I'm going to do is I'm going to show you that he's wrong and I'm right. Children, please don't learn this. You need expert to teach you this before you can do this thing, like standing on this table. Now I'm going to do this simple experiment and I'm going to drop these 2 pieces of paper that I've cut up in the shape of a letter T, but I'm going to drop them this way. And I want you to see which piece will reach the floor first. Is it fair if I drop it down this way? No, it's not fair. Is it fair? Or should it be this way? I think it should be this way and not this way. This way is not fair because it has an added advantage. It is already so much shorter, so I have to put it this way and I'm going to let this drop. Oops. First experiment failed. So, science experiment always fails. Redo it again. Redo it again. And show you all over again.
properly. Maybe I don't climb up because it's very naughty to climb up. And I'm going to show you the opposite. That if I were to do it this way, both about the same height, should reach the floor at the same time. But the reality is that it may not be true. Let's take a look at... Oh, by the way, I didn't introduce myself. I am not Phua Chu Kang. I'm just Phua Kang. Okay. 1, 2, 3. Did you see that they are different? Or maybe if I just use one piece, if it's this way, should have it. And I will let you see, look at it. If it's this way, do you see that the speed is different? So why is the speed different when the scientists have said that they should all drop at the same rate, but my experiment shows that it's different rate. Why is it so? So whenever there is school, there will always be homework. You will go home and look up the internet or read up books and tell me the reason tomorrow. Thank you. Any questions from anyone? Yes. With a styrofoam ball. I did not try the experiment with a styrofoam ball because the ingredient today doesn't include a styrofoam ball. Yeah, I should try, yes. Thank you. Any other question? No question? I'm very happy. Go home and see Rosie. Tata!
Our next contestant is Mr. Jake Ahmad.
Okay, class, you see this little balls that we have here. Now these are not ping pong balls. Right? These are very special balls. They're so special they have the words written on it. And these words are, you find the words written there. The letters are L, I, G, H, and T. Alright, these balls are very special because you know that today actually happens to be, I'm going to tell this story because behind every story, there's something to be discovered. See, exactly 100 years ago, this person created this phenomena, and his name is, he's a very, very humble person. So he would like his name to be rearranged. Right? He actually is, we remember him as Dr. Lemron. Okay, Dr. Lemron used these balls, and it was discovered 100 years ago, even before the game of ping pong. Where it's only there's no bats, and you notice here what these balls can do. And the letters here are very special because these balls, like I say, it's not ordinary balls. They're so light. They're very, very light. Okay, they're so light that if you bounce it from here, it goes up here. Then, but Dr. Lemron was able to do it with a very magic way, right? He created this magic mirror, right? You can see that it's so special that it's actually transparent. You take this mirror, and then you put it down here. Can you see the mirror? Can you see the mirror? But it's very special. It's an invisible mirror, right? Put the mirror over here, and what he did is that you just hold one ball. Okay, you take any one of the balls, right? You hold it up here, right? And if you just throw it, right? And what happens he finds that if you throw it fast enough, then you can actually catch the ball in an instant like that, and like that, very fast. You know how fast it is? Can you imagine how fast it is? You always have a lot of questions. How come you have no question today? Okay, how far did you throw it? You see, there was no sound. It's very much faster than the speed of sound. Very, very fast. It's so fast that you can't even see. And the trick why you cannot see it, let me do it one more time. I think the trick is that if you see it, now let me turn around and see whether you can see it. The problem is that looking at my face. Okay, when you look at the ball, don't look at my face. I'm going to do it the other way around. You see it this way, right? It's so fast that when I throw it, it just goes from one hand to the other, one hand to the other, one hand to the other. See, I catch it. Do you see it? Can you see it? Now you still cannot see it because sometimes you have to use the word that we will mention, imagination. Imagine you are a fast camera, okay, very fast camera, and you freeze a moment there. Now if you still can't see it, I'm going to use the last saying that this is actually passed down from Dr. Lembong. Like I say, he was so humble that he only wants his name to be reviewed 100 years after right of today, and he actually had his name rearranged. Okay, what's going to happen is I'm going to get yourself off the distraction of my face, right? You're going to look at the ball, right? And you're going to imagine you got a ball on my right, and it's going to go this way and this way and this way. Great. Can you see it? Right? What happens is if you put a line here, right? And then the trick here is that, according to Dr. Lembong, you must put the ball, right, such that the angle of my right hand to my body, right, this angle of right hand to my body must be exactly the same as the angle of the other hand to the body, which means this angle has to be exactly the same as this angle, right? Then, with the line here, actually the center line is 100 years later, Dr. Lembong's name can be reviewed. He's actually just a very normal person. This line is called a normal. Then you find that the angle of the hand here and the hand over here is exactly the same. The ball is going to bounce from the mirror and get caught here, and thus this is exactly how light travels, and it actually bounced off the mirror, right? And it was discovered that this light ball is so light, right? If you bounce it right enough with the angle, let's call it I, and the angle, another angle, call it R, exactly the same angle, it will actually fit. Now class, this, if you don't believe that it can be done, the first boy who can run down here, right? To do this, right, you will get these special balls which you can show to your friends. Anybody game in how to come down? Come on, you got 30 seconds, 15 seconds. Okay, time is up, never mind. Right? When these balls get bounced off, right, I do say, like I promised you, Dr. that his name is reviewed, actually his name is just simply spelled backwards, right? And this bouncing off, it sounds so primitive, he actually gives a very nice name called the reflection of light. Okay, second, just remember that light particles, they are simply like light particles, they get blown up, and they actually bounce off straight. But the important thing is that both angles to the normal has to be the same. Any questions?
Why must I equal R?
Why must I equal R? Otherwise you can't catch the ball. You have to be very fast. But that's what was discovered. Right? You will not catch the ball because if you have somebody stand over here, right, and the I is not equal to R, you actually cannot catch the ball. And this is how the light rays travel. It must be exactly the same. Any more questions? The balls are the light rays.
So we have one more.
Okay, it's actually a simple lesson on the effect of light striking a straight line and bounce. The term reflection is better explained with something that is familiar, and it bounces off. Right? It's actually a lesson on the reflection of light. So the story and the effect of the ball bouncing is from a very familiar situation, and with the imagination of the speed of light, leading towards the explanation of reflection of light, which I think the main theory is that the angle of incidence is equal to the angle of reflection. That was supposed to be a previous lesson that they didn't know that light travels in a straight line, so it leads to this bouncing off. Yeah, that was a pre-lesson. Okay. Yes. Yeah, we assume light travels in a straight line. And the imagination of speed of light by the ball.
assume you want to make a shorter path.
Yes, all these assumptions is made because this is assumed at the secondary level, and they will. Main emphasis was to teach that angle on screen is angle of reflection.
Okay, thank you very much.
Good afternoon to everyone. I'm Tan Peng Yon from Woodland Secondary School. Now today what I'm going to talk about is center of gravity, a lot of center of gravity, a few demos. Now, firstly, what is center of gravity? Center of gravity is defined as a point, right? Remember, it's a point whereby the whole weight of the object seems to act on. So what happens if I have a knife here and I put my hand to support here, you find that you'll drop this side because the center of gravity is here. Yeah, if I put my hand here, it will drop here. Now, what happens if I can support at the center of gravity? Yeah, the center of gravity is actually here, pre-marked. So, firstly, how to find the center of gravity, right? Let me explain. What we can do is put our two fingers by the side, slowly close up the gap, slowly, cannot be too fast. You find that automatically your two fingers will go to the center of gravity. The boys over there, you can use your pencil or pen or umbrella to try. No problem, it will work. Now, what is the reason? Now, the reason being, the center of gravity when it's near to one side, the weight, the distribution of weight is closer to one side, and therefore it applies a force down. With that force, you'll find that the friction will increase, right? Am I right to say that with a piece of paper here, you pull it easy, but with a weight on the paper, it's more difficult to pull, right? So same here, with this particular, when my hand is here, this handle here is more heavy because there are more material. So when I put here, you find that my left hand will tend to move first because there are less force acting on it and therefore less friction, right? When this one goes to a certain extent, when it's too near to the center of gravity already, then this hand will start to move. Yeah, eventually they'll come to the center of gravity. Now, once the center of gravity is reached and you support there, this kind of phenomenon we call it equilibrium, right? Equilibrium, there are three main types. The stable equilibrium, unstable equilibrium, and neutral equilibrium. Now, stable equilibrium is normally represented by having a support or pivot point above the center of gravity. So once you displace it slightly, you find that the center of gravity goes up. This is the characteristics of stable equilibrium. It will go up and you always come down to its original position. Stable equilibrium. Unstable equilibrium is when you hold it below the center of gravity, pivot it. You find that when you slightly displace it or disturb it, the center of gravity will come down and you will continue to go down until it goes to another more stable position. This is unstable equilibrium. Another type is neutral equilibrium, whereby you pivot it at the center of gravity. This particular position, when you start to disturb it, you find that he will just stay where you want him to be. He will not go anywhere else. Yeah? Now, with that, let me ask you a simple question, and you tell me whether this is what kind of equilibrium. What you need to do is your simple fork and spoon, put them together this way, right? Put a toothpick through it, then hold it, you find that it will stay. Now, to make it more interesting, you can take another toothpick, try to support it this way. Every time when the teacher do demo, normally we put 2 sets, especially you know that may not work. Yeah, that's what I learned throughout my 6 years of teaching experience. But sometimes the second set may also not work. Murphy's law. Okay, I think I will not go on this one, but I think you've seen just how it balanced. Later I'll show it again, hopefully I have time. So, you find that when you balance this way, it's quite interesting. Alright, when you slightly displace it, you'll go back to its original position. TJC, yeah. What equilibrium is this? Stable, unstable, or neutral? Neutral. Does it go back to its original position? Does it stay there? Good, clever. Change very fast. Okay, now, I'll do the last thing. Now, things are normally balanced. When they are balanced, you find that they don't move. But what happens if they don't balance? Interesting things may happen. Now, what I have here is 2 chopsticks and a ball. Normally, when you hold it, support the CG, it will stay there, don't move. But what happens if you slant it, you put it on a slope, it will drop, right? Drop. Now, what happens is, in certain circumstances, it will actually roll up. Yeah, it will roll up. And the reason, please go and think about it. Thank you. Please ask questions. I think science teachers have problems because the students don't really ask questions. We don't know what you are thinking. It will help the science teacher if the students start to ask questions. Do you want to know why it goes up? Do you know why it goes up? Now, this thing has a trick. You can play when you're eating fishball noodles or what. You can actually play. We use a big enough fishball. Make sure it's round. So what you do is, you put a fishball here, you find that you are actually not supporting the center of gravity. If you look from the top, it's here, the center of gravity is somewhere here. If you look from the side, the supporting point of this thing is actually somewhere here. So it starts to roll. Yeah, because it's supported here, the center of gravity starts to roll here. It starts to move. So when it moves, it actually, what you see is moving right, it's actually moving downwards. It's actually moving downwards. It seems to be moving right because the 2 chopsticks is in this inclination, but actually it's dropping inside. So this particular experiment is good to talk about principle of movement and actually talk about energy, conservation of energy. To make the students see, hey, why go up? Impossible. Then they'll start to. Thanks.
Thank you very much, Mr. Tan. Okay, our next contestant is Ms. Tan, Lydia Tan from Mahabodhi.
Good afternoon, judges, ladies and gentlemen, boys and girls. I'm Lydia from Mahabodhi School. I have to confess that I'm a biochemist by practice, so physics is not my cup of tea. So in here, just for today, I'm just going to demonstrate a technique to explain a concept. Okay? My subject interest is ping pong ball, as you can see here. And I'll be using them to demonstrate the density of various liquid based on the flotation of water. So density, if you could recall, in classes taught usually using solid. So the common example would be teacher using a ping pong ball and show flotation, or they want to show sinking, they will use a marble. What about the density of different liquid? Classic example is using oil, water, and they show the interface because oil being less dense to be on top of the water. But that's about all. What about other liquid? Okay, so okay, if you're going to use salt water itself and just water, it's almost impossible to see the interface. First, you need good skills to layer them. Secondly, over time, the liquid will actually form a homogeneous solution. Alright, so I'm just going to use the ping pong ball as a vesicle so that this concept can be more easily demonstrated. So because of time constraint, I have already prepared my ping pong ball filled with things like sisal. If you can see from here, I'm sorry, I didn't realize that the ball is going to be that big. So I already filled it up with things like alcohol, water, oil, sisal. So I'm using a variety of liquid here. I'm going to show density based on the flotation, based on their flotation in water itself. So if I can just show you a demonstration on how I can actually, just now previously there's a participant who tried really hard to pierce it. Trust me, use a syringe and a surgical needle, it helps. So all I have to do is to use all different kind of liquid from the end. After a couple of practices, I realized it takes in 30 ml of water. So I could have used this syringe that's a little bit bigger, but bear with me for a while. It's very simple. It takes just 30 seconds. Okay? And in the class, you can actually allow the kids to do that on their own. You have to take note here that you do not have an air bubble. And then the next question you may ask me, how do I seal the opening? Very simple. Using Vaseline. Okay? No tricks here. Oops, sorry. It can be found in any pharmacies. All you have to do is to dab it on. Okay. So what do you think? I've shown you the the ping pong ball itself, it floats. What do you think would happen to the ping pong ball that's filled with water itself? Anyone? Do you think you'll float? Do you think you'll sink? You think you'll sink? Okay, you'll sink a little. What about things like, okay, bear with me a while. What do you think would happen to the ping pong ball that's filled with dissolve? Okay, just to tell you that water, the specific density is at 1,000 kilograms per cubic meter. So what do you think would happen to things like dissolve? Would it float? What do you think? It float. I always say that. This is prepared dissolved ping pong ball. Floats. Okay, and I have things like the vinegar. What do you think about? What do you think would happen to vinegar? Let us think. In fact, I would like to show you something. If you look at salt itself, between salt and vinegar, these two have a specific density greater than water. I would like you to observe how the sink in water, the speed. For salt itself, it goes straight down to the bottom, and for vinegar, it actually takes some time to go down. So again, that is explained by the difference in the specific density. So of course, I have things like vegetable oil. Okay, and I don't know what happened to my ping pong ball filled with ethanol. Actually, went a little bit deformed, but it should work. Okay, it should be the one float. It should be the one the most less dense of all. All right, sorry, I have no idea why. It could be because of my car just now. So anyway, if you can use a simple experiment like that to show your class, you can ask them to even bring things like beer, milk, anything. Okay, you can include the kids to fill up the ping pong ball, and they can do the demonstration themselves. With this, I thank you.
Lydia, we can take some questions.
If you use ethanol instead of water, what do you mean by liquid ethanol? How many percentage is that? So 50%. It was still float. It was still float. Yes. Sorry, I think I do. You're talking about me using it in the physical itself, or just pouring straight into the water? Okay, what happened is that it will be less than yes, but then over time, as I say, it will form a homogeneous solution. Yeah. So if you're teaching in a class, you may not be able to show the interface. You may not be able to convince the kids that look, there is there's a different intensity between water and the ethanol.